The workhorses of the urinary system are the kidneys, which are the twin, bean-shaped organs in your body that clear harmful substances by filtering the blood. It's a bit like a water purification plant that helps to clean the drinking water for a city. Blood filtration happens inside over 1 million nephrons scattered inside each kidney, and each nephron is made up of a renal corpuscle and a renal tubule. So let's zoom in on the renal corpuscle, which is where blood filtration starts. The renal corpuscle is made up of the glomerulus, a tiny bed of capillaries, and the Bowman's capsule surrounding the glomerulus. Between the glomerulus and the Bowman's capsule, there's a space, called the Bowman's space. Blood gets to the glomerulus through the afferent arteriole, but interestingly enough, once the blood leaves the glomerulus, it doesn't enter the venules. Instead, the glomerulus funnels the blood into the efferent arterioles, which divide into capillaries a second time. These capillaries are called peritubular capillaries because they're arranged around the renal tubule. Now, the first step in blood filtration happens at the glomerular filtration barrier. The glomerular filtration barrier is made up of 3 layers, and together they separate the blood inside the glomerular capillaries from the fluid in the Bowman's capsule. They work like a sieve, allowing water and some solutes in the plasma, like sodium, to pass into the Bowman's capsule, while keeping red blood cells and plasma proteins in the blood. Starting from the capillary lumen, the first layer of the glomerular filtration barrier is the endothelium, made up of glomerular capillary endothelial cells. These cells have things called fenestrations, which are like pores in the cell themselves, tiny spots where the cytoplasm isn't filled in, so that solutes and proteins can't pass right through. But the fenestrations are so tiny that they block red blood cells from passing through. And blood minus red blood cells is called plasma, so plasma gets to the second layer of the glomerular filtration barrier, which is the basement membrane. The basement membrane is a gel-like layer with tiny pores, and this layer prevents plasma proteins from passing through. That's because the pores are too tiny for plasma proteins to slip through, and because the basement membrane has a negative electric charge, which repels the negatively charged plasma proteins. The third layer of the glomerular filtration barrier is the epithelial layer, which is made up of special cells called podocytes that wrap around the basement membrane like the tentacles of an octopus. Between these tentacle-like projections are tiny gaps called filtration slits. This third layer works with the basement membrane to block the passage of plasma proteins. The fluid that manages to get past all 3 of these membranes is called the glomerular filtrate. Now, the volume of fluid that gets through the glomerular filtration barrier is ultimately governed by Starling forces. Starling forces include both hydrostatic pressures, which are fluid pressures, as well as oncotic pressures, which are the pressures based on the amount of protein that's present on either side of the barrier. So let's zoom in and take a closer look at the spaces in question: the capillary blood and the Bowman's space, with the Bowman's capsule on the end there for reference. Now, since there are no proteins in the Bowman's space, there are only 3 Starling forces at play, and these are the hydrostatic pressure of the capillary blood pushing against the endothelium of the barrier, which we will refer to as PGC. Then there's the hydrostatic pressure of the filtrate in the Bowman's space, which we will refer to as PBS, and the oncotic pressure determined by the concentration of proteins in the capillary blood, which we will refer to as PGC. Together, these 3 pressures determine the net ultrafiltration pressure of the glomerulus, which is the difference between the force favouring filtration, which is the hydrostatic pressure in the glomerular capillaries, or PGC, and the 2 forces opposing filtration, which are the hydrostatic pressure in the Bowman's space, or PBS, plus the oncotic pressure in the glomerular capillaries, or PGC. So the net ultrafiltration pressure is equal to PGC minus the sum of PBS plus PGC. Now, let's think about the net ultrafiltration pressure at different points along the glomerular capillary. Early on in the capillary, right around when the blood flows in from the afferent arteriole, oncotic pressure is at its lowest because the capillary is still full of fluid, and that means that the protein concentration is relatively low. As blood passes through the capillary, fluid is filtered into the Bowman's capsule, so the concentration of proteins in the capillary increases, and, as a consequence, oncotic pressure increases as well. By the end of the capillary, right around where the blood is ready to flow into the efferent arteriole, oncotic pressure reaches a maximum value, and that makes the net ultrafiltration pressure approach zero. This point is called filtration equilibrium, and from this point on, there's no net shift in fluid in either direction, going towards the Bowman space or going towards the capillary. In other words, once filtration equilibrium is reached, blood is no longer filtered by the glomerulus. Net ultrafiltration pressure directly determines the glomerular filtration rate, which is the total amount of filtrate produced by all the glomeruli in both kidneys in 1 minute. Glomerular filtration rate can be worked out as the net ultrafiltration pressure multiplied by the filtration coefficient, or Kf. Kf indicates how permeable the capillary is to fluid, and it depends on the surface area that's available for fluid filtration, as well as the permeability of the glomeruli. The glomerular capillaries actually have a relatively high filtration coefficient when compared to systemic capillaries, because the glomerular capillaries are all huddled together like a ball, and this increases the total surface area for filtration. And also remember that the glomerular capillaries have fenestrations. The glomerular filtration rate can vary based on changes in any of the 3 Starling forces. So let's go through them. First, let's look at capillary hydrostatic pressure, which is mainly determined by the resistance of the afferent and efferent arterioles. Now, if there's vasoconstriction of the afferent arteriole, this reduces renal blood flow, and in turn, capillary hydrostatic pressure and the glomerular filtration rate, or GFR. If there's vasodilation of the afferent arteriole, there can be the opposite effect: increased renal blood flow, increased capillary hydrostatic pressure, and an increase in glomerular filtration rate. Now, if there's vasoconstriction of the efferent arteriole, that decreases renal blood flow. However, since the increased resistance is after the glomerulus, there's more fluid inside the glomerular capillaries, and that leads to an increased hydrostatic pressure and therefore glomerular filtration rate. If there's vasodilation in the efferent arteriole, that increases renal blood flow. But since the blood encounters less resistance exiting the glomerular capillaries, there's a decrease in hydrostatic pressure, and therefore a decrease in glomerular filtration rate. Second, let's look at oncotic pressure. An increased concentration of proteins will lead to an increased oncotic pressure, and that leads to a decrease in glomerular filtration rate. Conversely, a decreased concentration of plasma proteins has the opposite effect. There's a lower oncotic pressure and an increase in glomerular filtration rate. Thirdly and finally, there's hydrostatic pressure in the Bowman space. Now, if there's a blockage in the urine flow, like a stone that's lodged in the ureter, blocking the drainage of urine, then the backup of urine can cause an increase in hydrostatic pressure opposing filtration. An increase in hydrostatic pressure in the Bowman space leads to a decrease in glomerular filtration rate. And typically, there aren't really any situations that cause a decrease in hydrostatic pressure in the Bowman space. Alright, so let's wrap this up with a quick recap. The glomerular filtration membrane sits between the blood and the Bowman space. The glomerular filtration rate is the amount of blood filtered each minute, and it's determined by 3 Starling forces. These are capillary hydrostatic pressure, capillary oncotic pressure, and hydrostatic pressure in the Bowman space. Together, they determine the net ultrafiltration pressure, which is the main determinant of glomerular filtration rate, along with the filtration coefficient, or Kf.